Morning, everyone. I hope you're doing well. Uh, so fortunately, we got ahead to then get behind, right, with this weather. So that this time of year is always a little funky um, with weather cancellations. If we were in person, you've been at AV Tech, you've probably been used to that, where they've canceled class, when there's no snow anywhere. Well, at least not at the campus, but there are people who live in different areas, so they get snow. I don't know. I'm from Chicago, so I'm sort of bitter about the cancellations. I'm like, you should be walking 3 miles in the snow uphill, but that is not the case. Um, but because we're all online, it's kind of weird, but we still have to honor the cancellations of the campus. Because I actually, even in this class, I have quite a few students who don't have reliable internet and they're using campus internet. So if they can't get to the campus to use the internet, we can't have class. So that's why the cancellations are happening. I have been sending, let me share my screen. I have been sending those sorts of notifications and such through the announcements page. So there's a forum on here called announcements, and I force subscribe everyone in the class. So you should be getting an email every time I send an announcement that has like the cancellations and things like that. If that isn't the case, you need to go into your preferences in your Moodle page. It'll show you up here by your name. You'll have to go to preferences and go to message preferences and notification preferences. I'm not sure which one it is, but one of them go down to, where is it? Forum, system quiz, questionnaire, open forum, forums. So just make sure that your emails are clicked on with the subscribe posts. Okay. If you haven't gotten the email, that's where it will be. Even though we got ahead to get behind, we should end up finishing up just on time for you guys to be able to complete your test, which starts on Sunday at 5 a.m. and expands to Monday at midnight. Some common questions. Do you have to take it in one sitting? Yes. You can't just sort of answer a question and then like leave and then come back and answer a second question. You got to answer them all. And because of that, you are going to want to study because you don't want to sit down and have to teach yourself chemistry. So have a good working knowledge of it. Now, with that being said, you do get to have, a little bit of help. So normally I would have things like, the heat of vaporization energy, heat of fusion. These would be numbers that you would have to have memorized. You don't have to have them memorized, but I would consolidate them onto a worksheet or a piece of paper with all your other formulas and, periodic chart so that you can just access them easily. Okay, so speaking of heat of fusion, this is where we left off. So we talked about when you're phase changing, all energy goes simply to changing, all energy given or all energy released goes to changing it from one phase to another. There's no temperature change. So in these equations, we don't see a temperature change. If we want to, for fusion, right, to fuse, so that's indicating that we're talking about some sort of solid transformation. If we want to melt it, we have to add heat, specifically 80 calories a gram or 334 joules a gram. If we want to freeze, we have to release that much heat or give it up. So we already did this. Great. The other number that I want to talk about is, so if we boil water, water will go from a liquid to a gas. Bubbles will appear through the liquid. Those bubbles are actually trapped water vapor. So the liquid is turning into a gas and then it's rising up. We have sublimation. So sublimation and deposition. Sublimation is when you skip that middle liquid state. So you go from a solid to a gas, or deposition is going from a gas to a solid. You do want to know that definition. Dry ice is just the sublimation of carbon dioxide, CO2. So when you have dry ice, like at Halloween or something, it's just taking solid CO2 and then putting it into a gas. Okay, so heat of vaporization. This is another number that you're going to want to know. This is the amount of energy it takes to take a liquid from it, or take 1 gram of a liquid to a gas, or the amount of heat released to take 1 gram of that gas into a liquid. Remember, these numbers are very specific to the material. All right, so if we're dealing with like ammonia, it's going to have a different set of numbers than water. So the heat of vaporization of water, and water's boiling point is 100 degrees Celsius. It is going to be 540 calories a gram, or 2,260 joules a gram. So bigger number. It requires more energy to go from a liquid to a gas than it does to go from a solid to a liquid, which would make more sense. Gas has a lot of like bang for its buck. There's a lot of kinetic movement in there. So to get it up into that gaseous phase, you got to pump a lot of energy in. So know these numbers or have them around, right? So 540 if we're doing calories, 2,260 if we're doing joules. So go ahead and do this problem here. How many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? So a couple things, it's giving you a amount of steam in grams. It's asking you to figure out something about condensation. So that means you know you're going from a gas to a liquid. You're already at the appropriate 100 degrees Celsius, and it wants the information in kilojoules. So I'll give you just a minute, 2 minutes for that. Sorry about that. Hold on. Where did we go? There. Just another 30 seconds. Okay. So when you are at the correct temperatures of like a phase change, so if you're already at the 100 degrees Celsius, all you have to do is multiply the heat of vaporization by how many grams you have, right? It's that simple. There's no temperature change, so we don't need to worry about the Q equals MCAT, any of that mess. So we've got 50 grams of steam. We want to figure out how many kilojoules are released. So we need to go from the grams of water, 50 grams of water, or specifically steam. We need to use the heat of condensation, which is the same thing as the heat of vaporization. All right, that will pop it out in joules. And then from joules, we can get kilojoules. This step right here is just using that relationship of for every 1 gram of H2O, I need to release or absorb 2,260 joules. Remember, there is that other one related to calories. We're not talking about calories for this problem, so we can ditch that one. So because this is an equivalency, we can write it as a conversion factor, and we just want to make sure that we put it in such a way that the correct units cancel. So here we've got 50 grams of water. We're going to multiply it by the heat of fusion, or rather heat of vaporization, because we're in the gas to liquid phase change. I'm going to put the 1 gram on the bottom so that it cancels, and I'm going to put the energy on top, the 2,260 joules. And then the problem says, hey, I want it in kilojoules, so we're just going to throw a final conversion there on kilojoules. So for every 1 kilojoule, it's 1,000 joules. We should end up with 113 kilojoules released. The problem says how many kilojoules are released. The released means it's giving the energy out. So the water is actually losing that much energy. Just be mindful of the words. If we were going in the other direction, let's say we were a liquid becoming a gas, we would absorb that same amount of energy. So let's take the Q equals MCAT. So when we temperature change things and we phase change things all together into what's known as a heating curve. So if you want to draw one of these out, you can do something real simple. Just draw a graph, put temperature on the y-axis and put heat absorbed on the x-axis. You increase as you go up and you increase as you move to the right. So the first phase that we're going to be in is solid, all right? And this graph has it at negative 40 degrees Celsius. So you can start there. So let's say that this is, we're not even gonna say, it's for water. So I'd make a mark on your temperatures, make a mark at 0 degrees and make a mark at roughly 100 degrees. It doesn't have to be perfect, all right? This is just for a concept. So if I'm a solid and I'm at like minus 40 degrees, or I'm at anything below 0 degrees Celsius, I can't start melting that solid ice until I bring it to 0 degrees Celsius. So the first thing I need to do is increase my temperature. And what happens is I increase my temperature, I have to absorb some heat. All right, so I increase temperature and I absorb heat. Now the flat areas on this graph, there's 2 of them here. Those are phase changes, okay? So diagonals are temperature changes, flats are phase changes. So what's happening at this first thing when we get to 0 degrees? And this will sort of explain it step by step as well. But when we get to this flat area, all the heat that's absorbed, I'm still absorbing heat as I move from left to right. All the heat that's absorbing is going into changing it from a solid to a liquid. Do you guys see how at the flat ones, we're not increasing our temperature? The temperature stays consistent, right? The temperature stays at 0 degrees because any added heat is going to changing the phase. Now, what happens when I become a liquid? Once everything is a liquid, we're not going to phase change. We're going to increase temperature as we absorb heat. So I'm absorbing heat and my liquid is increasing in temperature. So this is like, you have freshly melted ice sitting on your stove. And now we want to boil that. So you've got to, before you can actually get to the boiling phase, you have to take your liquid that's at 0 degrees, you have to increase the temperature. Okay, so we've got another one of those angled slopes. We increase the temperature until we get to 100 degrees. Once we get to 100 degrees, that's when we can start the boiling process where all added heat phase changes. You see how this is again flat? Why is it flat? Because the temperature isn't changing. It's staying constant at 100 degrees. We're just taking our liquid and turning it into a gas. Once we get to the gas, we can then increase the temperature of the gas. So you've got this curve here at the slopes. all right? Anything that's angled, that's where you're gonna use Q equals MCAT, MC delta T. Okay, Q equals MC delta T. Q equals MC delta T. Think about what's going on here. There's a temperature change, right? In this one, we went from -40 to 0 degrees. So we have a temperature change, so we need to use the equation that has the temperature change. At the flats, these are phase changes. So flat is a phase change. Specifically, this is boiling. So this is heat of vaporization. What's going on over here at the melting? This flat is also a phase change. This is a phase change, but this is heat of fusion. So heat of fusion will be applied anytime you're going from a solid to a liquid. Heat of vaporization will be applied anytime you're going from a liquid to a gas. It doesn't matter in which direction you're going. If we're heating it up or if we're cooling it down, we can still use the same numbers. What changes? The sign or the wording. If we're going up the curve, we are absorbing heat, or it's a positive energy value. If we're going down, we're releasing heat, or it's a negative value. So now we can combine our Q equals MCAT with our heat of vaporization, because let's say we have a liquid and I want to boil it, but I'm not at 100 degrees. Let's say I'm at 60 degrees. The first thing I'm going to need to do is raise the temperature, then I can phase change it. We will do some practice with this. This is a cooling curve. A cooling curve is just the opposite of a heating curve. You start with a high temperature, you start to release heat. Oops, I'm sorry. You've got to release heat until you get to that magic boiling condensation temperature. And since we're talking about water, it's at 100 degrees. Then you have to release enough heat to transition from water, or rather steam to water. Then you cool your water, then you can freeze, then you can cool your ice. So you can't take your ice and drop it down to minus 20 degrees until it's all ice. If there is any remaining water, any heat released will go into the freezing process. You've got to freeze it all up first. So just a concept thing here, a plateau or a horizontal line on a heating curve represents a constant temperature, right? So let's go back. These flats or the horizontals, no temperature change, right? We're not dropping, we're raising. A sloped line on a heating curve represents some sort of temperature change. So you can even go a little further and say for the plateaus or the horizontal lines, that's going to be heat of fusion or heat of vaporization, depending on, what phase you're going to and from. Sloped lines, there is a temperature change. At the plateau, there's also a change of state as well. A constant temperature and a change of state. Here we have a slope line is a temperature change. This is where you have Q equals MCAT, MC delta T. Anytime you're changing your temperature, you use Q equals MCAT. A flat line on a heavy, okay, yeah, so there we go. Use the cooling curve for water to answer the following questions. So if we're looking at the cooling curve for water, water will condense at 100 degrees Celsius. Condensing meaning it's going from a gas to a liquid. A temperature of 0 degrees Celsius, liquid water begins to freeze. At 40 degrees Celsius, water is, well, let's go back to the chart, right? At 40, we are a liquid. And then when water freezes, heat is, so if we freeze water, heat is being removed, right? Anytime you're going colder, you're removing heat. So it may be useful to actually have this one for water accessible to you somewhere or draw it out. Okay, so let's look at a problem. So this says calculate the total heat in joules. And I'm going to go through this one step by step, and then I'll give you one to work on your own. So calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees Celsius to gas at its boiling point of 78.0 degrees Celsius. Ethanol has a specific heat of 2.4 joules per gram degree Celsius and a heat of vaporization of 841 joules per gram. Oh my gosh, there is like so much information in there. This is talking about a heating curve. So the first thing we're going to want to do with this thing is to draw a heating curve. Split screen this here a little bit. Go to our class. Okay. So whenever I have a problem like this, what I like to do is to draw just sort of like a basic heating curve. It doesn't have to be perfect, but something where I can put my numbers in. So calculate the total heat needed to convert 15 grams of liquid ethanol at 25 degrees Celsius. So my ethanol is currently at 25 degrees Celsius. So I'm going to put a point, my starting point. And I'm going to put 20, let me make that a little bit thicker. 25.0 degrees Celsius. Okay, so that's my starting point. Now I want to take, this is liquid. So I can even write underneath it that at this temperature, it is a liquid. I want to boil it, but in order to boil it, I need to get to 78 degrees Celsius. Can I boil at 25 degrees Celsius? No, I have to first get it to its boiling temperature. So I have to do a temperature change, or I have to bring it from 25 degrees Celsius up to 78 degrees Celsius. What is a temperature change? Are your temperature change your flats or your slopes? Temperature changes are your slopes. So I'm going to make a slope, and my ending point is going to be that 78.0 degrees Celsius. So that's sort of step one. Step one is taking my liquid at 25 degrees Celsius and bringing it to a liquid at 78 degrees Celsius. Now what's next is it says, hey, let's boil this bad boy. So I want to take it from a liquid into a gas. That's a phase change. Phase changes are going to be flats. All right, I'm going to go from a liquid to a gas. Remember, what is liquid to gas or gas to liquid? That is heat of vaporization, right? Fusion is solid, liquid, liquid, solid. So we're trying to go from a liquid to a gas. And then we have a bunch of additional information. So for ethanol, here's its heat of vaporization, 841 joules per gram. So I'm just going to write that next to here, 841 joules per gram. Remember, these numbers are unique to the substance. So because this problem is talking about ethanol, I can't use any of the water ones. All right, so we've got 841 joules per gram. What other information do I have in here? I have the specific heat of ethanol. The specific heat of ethanol is 2.46 joules per gram degree Celsius. Remember your angles are going to use Q equals MC delta T. So I better know what C is. And in this case, we said C is 2.46. 2.46 joules per gram degree C. Is that making sense so far, where I came up with that drawing? If it's not, if there's any questions, let me know. There are people who definitely can solve these without making the curve in the drawing. I like to do the drawing even today, even now, because I just feel like it helps organize all the information. So every slope and every flat is going to be a step. So this is a two-step problem. I'm going to say that this is step one. And then let's say that the flat up here is step two. So for step one, now that we've got all the information, I can expand this out. Step one is to go from liquid 25 degrees Celsius to liquid 78 degrees Celsius. It's a temperature change. So this is a slope. Slopes need Q equals MC delta T. You're solving for Q. We're solving for all the heats of all these different steps. So let's go ahead and write that out. Q equals, well, what is our mass? I didn't write that down. It should have been in there in the problem somewhere, right? Was it 50 grams? 15 grams. Okay, so we have 15 grams. So my mass is 15 grams. What is my C? My C is my specific heat for ethanol. And remember, we wrote it down here. So if you get this slope or heating curve all organized, the information just sort of falls into place. So we've got 2.46 joules per gram degree Celsius. And then we have our temperature change. So the temperature change isn't calculated yet, but you can do it really easily. Remember, final minus initial. So it's going to be 78 minus the 25. 78 degrees Celsius. Pull out my calculator. Addition and subtraction is like the hardest thing for me. So 78 minus 25. All right, we've got 53. So 53.0 degrees Celsius. I feel like that was 15.1 grams or 15.0 grams. Yeah. So let me give this another significant figure, 15.0. 53.0 degrees Celsius. And then, oh, and that's it. Okay. So we're just going to calculate this out. So grams will cancel, Celsius will cancel, and we'll be left with units of joules, which we like. 15 times the 2.46 times the 53, 1,955.7. I'm going to keep all, and this is in joules, I'm going to keep all those, and I'm just going to, this is 3 sig figs. So 1, 2, 3, I'm going to just put a line right there to remind me I only can really honor 3 sig figs. That's step one. Is that clear how to do that? That's just a simple Q equals MCAP. Cool. Awesome, Astrid. All right, so let's do the second step. So 2, step 2 is the phase change. That one is actually a little bit easier to do. We don't have to worry about temperature change. We don't have to worry about specific heat. All we're doing here is taking the mass that we have and multiplying it by the heat of vaporization. So our mass, we said, was 15.0 grams. We're going to multiply that by the heat of vaporization, and stay there. 841 joules per gram. Okay, so 841 joules are needed to heat 1 gram of ethanol. What happens to the grams? They'll cancel and we'll be left with just units of joules. So 15 times the 841. And we get a really big number, 12,615 joules. These phase changes in general, when you're going from a solid to a liquid or a liquid to a gas, usually are a magnitude greater in how much energy they require than the temperature change. So what is the final step here? The final step is I've got to add it all up, right? So this was a 2-stepper, so I just need to add 1 plus 2. If I had like 4 steps, I'd have to add 4 of them together. So I'm going to take my 1955.7 joules, and I'm going to add it to the 12,615 joules for a total value of 0.7, 14,570.7 joules. As far as sig figs are concerned, this had 3 sig figs. Okay, so this was to the 10th place in hundreds. So I can go with 14,600 joules. Did the problem want it in kilojoules? I don't even remember. Sometimes these problems want it. Calculate, no, it says joules. Okay, calculating. Sometimes they like it to be in kilojoules because these numbers can get pretty big. So if we wanted to convert this to kilojoules, here's the decimal, move it over 1, 2, 3, it would be 14.6. Whoa, 14.6 kilojoules. So depending on what. So not too bad, right? I think these aren't too bad if you can get this concept here. This is like the magic part of the problem, is getting your heating curve together. Otherwise, the problem just feels like a slop of given information and you don't know what to do. Can you have problems that are longer than this? Yeah, you could have like a solid that needs to be heated up and then melted, and then that needs to be heated up, and then it needs to be turned into a gas, and then that needs to be heated up. You could have like a 5-step problem. Probably won't give you a 5-step problem, but a 2-stepper or a 3-stepper is not uncommon. So let's have you do one on your own. This is exactly what we did, right? Raise it up, and then you can phase change. Here are your values. 19.6, is that what I had? Oh no. I had 14.6. Oh, they didn't add it together yet. Right, and they had the second component, so 14.6, yes. Okay, good. I'm about to embarrass myself there. Okay, so here's a problem that I want you to do. It gives you a couple answers, but that doesn't really matter. Just solve it like you would the last problem and then pick. Okay, so a volcano erupts. 175 grams of steam at 100 degrees Celsius is released. How many kilojoules are lost when the steam condenses and then it freezes at 0 degrees Celsius? This is talking about water, so you need to use your water equations. It's starting as steam. First, it needs to become a liquid, then the liquid needs to cool, then the liquid needs to freeze. Okay, so I want you to we're gonna break this up. I'm gonna spend 2 minutes just doing the heating curve. Just make the heating curve for it. And then we'll come back together, we'll do the heating curve, and then I'll have you do the calculations. All right. So the volcano erupts, there's 175 grams of steam. So I'm starting as steam at 100 degrees Celsius. So we're at 100 degree, 0.0 degrees Celsius. And if I'm steam, that means I'm a gas. How many kilojoules are lost when the steam condenses and then freezes? So I want to take this 100 grams of gas and I want to freeze it. So the first thing I need to do is condense it. Now, condensing means that I'm going from a gas to a liquid. And if I'm already at 100 degrees Celsius is the temperature that we can condense, right? If I was at 101, I'd have to lower it 1 degree. But since we're already there, the phase change will come first. So I'm going to draw a flat. And this is where I go from a gas into a liquid. Now, I want to freeze. So once I'm a liquid, if I want to freeze, I'm still at 100 degrees Celsius, right? I can't freeze my liquid water until I decrease its temperature to the freezing point. So I've got to do a temperature change and drop this all the way down to 0 degrees Celsius. Now, the last thing I need to do is I need to freeze it. All right, so I have to go from 0 degrees Celsius as, and I'm sorry, let me write this as a liquid because this is a liquid, into a solid form. So we want to change this into a solid at 0 degrees Celsius. Does it say we need to decrease it anymore? No, we can keep it at 0 degrees so I don't have to drop it again. So this is the liquid to the solid transformation. Gas to liquid, this is heat of vaporization. Liquid to solid, this is heat of fusion. Remember, slopes are your Q equals MC delta T. So how many steps do I have here? 1, 2, 3. Okay, so now I want you to solve the problem. So go ahead and work through step 1, step 2, and step 3. If you're wondering, well, where are these numbers of heat of vaporization? There are a couple slides back, or you can like look it up on your phone, heat of vaporization of water. The water ones you're gonna wanna have on hand. If I was to give you a problem like off of ethanol or some other material, I would give you those heat of vaporizations, okay? But do know the waters offhand. So I'll give you all about 4 minutes to work through solving that. If you have any questions on this drawing, let me know now so I can clear it up. And you can throw it in the comments or you can turn your mute off if you do. Okay, so I'm gonna clear up our curve here. So they have a cooling curve. They went in the opposite direction. So they started here and went over, down, over. It's the same thing as ours, right? We just have ours flipped. So step one, we have to take the steam at 100 degrees Celsius and turn it into liquid water at 100 degrees Celsius. So here's all the information that will need to be used in some capacity, right? With the specific heat of water. We've got 1 gram of water is equivalent to 2,260 joules. This is this heat of vaporization. We've also got the heat of fusion because we want to fully freeze it. So I don't like how that's organized. We said all right, so this is going from gas to liquid. This is liquid. This is going from liquid to solid, 0 degrees Celsius, 100 degrees Celsius. So first step is to, we've got, what step? 1, 2, 3. Step one is to condense. I think I had 175 grams. 175 grams, yep. So 175 grams of water. And I know for every 1 gram of water, it's 2,260 joules of energy that get released, right? So grams will cancel. This is a big number. This is a lot of energy released. We've got our 175. We multiply it by the 2,260, and I get 395,500 joules. Okay, that's step one. Step two, let's change our color. Step two, that's a slope, right? So slopes are Q equals MC delta T. We're solving for Q. So our mass is still 175 grams. Our C is our specific heat for water, which is 4.184 joules per gram degree Celsius. And then our change in temperature is 100 degrees. Specifically, it's minus 100 degrees Celsius because it's final minus initial, 0 minus 100. So that'll mean that this is a negative number, but all the signs are the same. This is technically a negative number as well because you're losing the heat, okay? But it's in the wording of the problem. That's one thing to note. So if you're going down a slope, all the numbers will be negative. If you're going up the slope, all the numbers will be positive. With their negative, that's just meaning it's going out into the environment. So we'll take our 175, multiply it by 4.184, and then multiply it by 100. So this gives us negative. Again, don't get freaked out by the negative. It just means it's going out of the system. So negative 73,220 joules. All right, last step is a flat. Flat is a phase change. So we take the mass, 175 grams, and we need to multiply it by the heat of, well, whatever going from a liquid to a solid is. It's the heat of vaporization. I'm sorry, the heat of fusion. And I forgot it. It's what, 334? Yeah, 334 joules per gram. So 394 34 joules for every 1 gram. The grams will cancel. Five 58,450 joules. This is again a negative number. So the last step is to add 1, 2, and 3 together. So add them all up. You can sort of just ignore the negatives. 73, 220. Okay, and I get combined value 527,170 joules. The problem wants it in kilojoules, so move this over 1, 2, 3. 527 kilojoules. Let's see if I did that correctly. No, 5,280. So did I round it wonky? 4. Yeah, that's close enough. Okay, this I didn't round in my intermittent steps, so something happened there where this isn't a 5. It's close enough. You'll get the problem. You'll get the problem right. So B for that one. Okay, so first we condensed, then we changed the temperature, then we froze. Any questions on that, on how to solve those? So I think for these, this is the key to success here, is getting your heating curve correct. Sometimes you could start with a phase change and then do a temperature change. Sometimes you start with a temperature change and then do a phase change, right? Any of those options are available. As far as, so Astrid, so the heat of fusion and the heat of vaporization are the only formulas we need to know for phase changes. Yes, for water, yes, know those, and know them for calorie as well, in case the problem is talking about calorie instead of joule. The heat of fusion and the heat of vaporization for any other material will be given to you in the problem. So do have the ones for water on hand. Other questions? Sig figs, are they important? So sort of, yeah, I mean, look, sig figs are really important when the problem is asking you about sig figs. Okay, so there will be some problems on this first test where it's like, round this to the correct number of sig figs. This problem down here, I'm not gonna have one that's like, 5,270 or 527,000, and then one that's 529,000. It's not going to be, or like an extra sig fig. I'm not going to do that for these bigger problems. It's going to be this number or a number that's substantially different from it. Okay. So sig figs are important on this test with the sig fig problems. Other questions? Okay. Well, if you have any individual questions, stay around. Otherwise, I will see you next Tuesday. Good luck on your test. Make sure you get that done. Yeah, have a good weekend. See you. Bye. Hey, Natalie, do you have a question?
Hello, I do. So I just had a couple questions regarding this week's lab.
Okay, lab 4, is it?
Yes, ma'am.
Okay, what question?
So the first one is B10. Just clarifying, that's the Q equals MC delta T, correct?
B10. Yes, so heat joules gained by the water. Yeah, so the equation you'll use for that is Q equals MCAT. So you should have your mass of water, you have your temperature change of water, and then you should know the specific heat of water just off the top of your head, hopefully.
Okay, awesome. And then question 4, I was just a little confused as to what it was asking me. I've always had a problem with word questions.
You and every other human being on the planet. So
Yeah. So I'd
okay.
written out given, um,
So
and I had actually,
are you saying are you looking at how many calories are required to raise the temperature of 225 grams of water from 42 to 75?
yes,
Okay. So if we're raising the temperature, which heat equation do we use if there's a change in temperature?
the Q equals MC delta T.
Yep.
Okay.
The only difference with this problem is it's talking about calories
Mm-hmm.
as opposed to joules. So you won't use the specific heat of 4.184 joule per gram degree Celsius. You'll
Okay.
use 1 calorie per gram degree Celsius.
Okay.
Okay.
All right.
But other than that, look, you've got your specific heat of water, you've got your amount of water, and you have your temperature change. So that's Q equals MCAP.
Okay. Awesome. And then my last questions. So I had actually missed class last week on Thursday.
Okay.
I'm taking 2 micro courses and then a social psychology class in addition to this. So I had to catch up a little bit.
Okay.
So it's basically part D. I am just, again, with the calories. So I had taken.
Okay. So like figuring out the kilocalories from the carbohydrate, fat, and protein?
Yes.
All right. So do you have a food sample?
Yeah. So I used trail mix, the
Okay.
serving size, and I've got all the stuff.
Okay, but you want to calculate the kilocalories.
Yes, ma'am.
Okay, so next to like over here on the side where there's a little bit of space, next to the carbohydrates, right? 4 kilocalories per gram, or like a fraction bar with 1 gram under it.
Okay, so a conversion factor?
Yes, exactly. So anytime you have a carbohydrate, doesn't matter what the carbohydrate's coming from, your trail mix or a banana, carbohydrates offer 4 nutritional calories per gram.
Okay.
Fat offers 9 kilocalories or nutritional calories per gram. That's why you don't eat a bowl of fat. You can eat a bowl of cereal, but you won't eat a full bowl of fat because it's just so calorically dense.
Yeah.
And then protein as well is also 4. Okay, so 4, 9, and 4.
Okay. So just in the sense of the actual equation, I would take my starting grams of carbohydrates and multiply that by the conversion factor and so on.
Yep. And then that'll give you the calories coming from carbohydrates. You do the same thing for fat and protein. And then to get your total calories, you just add the 3 of those up.
Okay. All right.
And your total calories will be, it'll probably be slightly off from whatever's on the back of the box. Like it may be like a couple calories off. That's fine.
Okay. And then for the percentage of the total calories, oh boy, this one, yeah, I'm not really sure.
So first you have to figure out how many calories you have for each.
Mm-hmm.
You have your total calories. So percent, you take the part divided by the total and multiply it by 100.
Okay. That's what I initially had thought, but I've always been unsure about that.
Yeah. So you'd calculate how many calories you have from fat, divide it by the total number of calories in the food, and then multiply it by 100 to get it into a percent.
Okay. Awesome. And I think that was pretty much it regarding the lab.
Okay.
So I appreciate that. Thank
All
you.
right. Yeah, no worries. Have a good weekend. Don't forget to do your test.
Oh goodness, I'll try
Okay.
try to do my best.
All right. I'll
See
see
ya.
ya.